Hello everyone. In this lecture we will start chapter 5, which is application of first law of thermodynamics. Okay. So first thing topic we will study in this is control volume energy analysis. Okay. In this the first topic is flow work or displacement work. What is flow work or displacement work? Okay, so let's consider an open system. So this control volume energy analysis is basically done for open system. And why for open system? In open system there is continuous flow of mass in and out of the system. So it is impossible to study a particular mass. Okay, because that mass at some point will not be in the a part of system. For such a system we consider control volume. What is control volume? So we consider part of the system, and we if we have, so let me draw a diagram first. Let's consider a system. So let's say this is a system, and there is inlet port and outlet port here. Let's say this is an inlet port, this is an inlet port, and let's say this is an outlet port. Okay, so for example, let's say a small element, like a fluid, let's say a fluid is flowing in and out of this control volume. Okay, this whole system, this whole part is here, control volume. So I, instead of focusing on a part of the fluid which is at one point inside the system, at another point outside the system, we focused on this control volume. Okay, this section, whatever fluid come here, we will observe that fluid. Okay, so here let's say a fluid particle or a fluid element, let's say a fluid element, or either it a fluid element or liquid element, whatever it is, a fluid element enters the system. So let's say this fluid element enters the system. Okay, and after certain time, after the motion, it exits the system here. Okay, so let's say at entry the pressure is P1, sorry, let's say at this point, at this location, the pressure is P1, and the specific volume is V1, and outside, like at this location, the pressure is P1 plus dP1. It should be slightly higher than the pressure inside, because only then the fluid element will move inside. Okay, and similarly at this side also, let's say here it is pressure of P2 and a specific volume of V2. Okay, now let's consider the energy of the system to be del U and the mass of element to be delta M. Okay, and similarly M1, and let's say since it is at entry, let's say having energy delta U1, and here it is du1, it is du2, and mass is delta M2. Okay, so we will so what is flow work? Flow work is the work required to move this fluid element inside the system. Okay, so we will be having two work elements here. First one, the flow work at entry. What is flow work at entry? Flow is a constant. So what is the formula for work done? PdV. Okay, so if we consider this fluid element, this fluid element, there is no motion of uh, like fluid from inside to outside or outside to inside in this element. Okay, so for this element it will act as a closed system. Okay, so the value of work done will be PdV. So here pressure is P1 plus dP1, and volume is dV1. That's it. Okay, delta V1. Okay, so we can write it as P1 delta V1 plus dP1 into delta V1. Now since this term is very small, we will directly neglect it, and so we can say here that delta W entry is equal to P1 into delta V1. Okay, now if we divide both sides by mass of the inlet element delta M1, what we will get? We will get the specific. So here it is capital W. Okay, now it is specific work at entry, which is known as displacement work. Okay, will be equal to P1, and this delta V1 upon delta M1 will be known as V1, specific mass, specific volume. Okay, so the work done at entry or flow work at entry is represented by P1 V1. Similarly, if we calculate it at exit, we will get flow work at exit is equal to P2 into V2. Okay, this is the flow work at entry and exit. Now the second point which we will study in this to control volume analysis is steady flow energy equation. Energy equation, also known as SFEE. Okay, so for steady flow energy equation analysis, let's again consider a system. So let's consider this is a system. Okay, and there is some entry point, and obviously there is some exit point. Let's say this is an entry point, inlet, and this is outlet. Okay, let's say this is location 1, this is location 2. Okay, location 2, location 1. Now I will define the control volume here. This this is called control volume. This will be control volume. Now if we consider, like let's say that the Q amount of heat is supplied to the system, Q kilojoule per kg, and let's say the system produces W amount of work, W or WCV. Okay, this is also in kilojoule per kg. Let's say the state at entry is the velocity is C1, pressure is P1, elevation is Z1, and specific volume is V1. Okay, H1 is enthalpy and U1 is internal energy. Similarly, at exit, C2 is velocity, P2 is pressure, Z2 is elevation. Okay, now V2 is volume, specific volume, U2 is internal energy, and H2 is enthalpy. Okay, now from energy conservation, from first law, we know that energy at inlet is equal to energy at exit. So we will equate energy at 1 and 2. Okay, now let's write it. So energy entry and energy exit. It is okay. So energy inlet, let's say which part of energy entering. So first you can say that at enter energy u1 the fluid is entering, having the speed of c1, and we will take here kinetic energy form, plus having potential energy gz1, plus having flow work for the entry element p1 v1. Okay, plus there is one more thing that is entering, which is the q amount of heat. Okay, and this will be equal to exit fluid is at u2 plus with velocity c2, having potential energy gz2, having flow work p2 v2. Okay, and plus there is one additional thing that is exiting from the system, that is work done wcv. Okay, now we know that from previous observations in previous topic, last lecture, that u plus pv we can write it as h. Okay, so in both cases there is the term u plus pv, so we will reduce this term and we will write it as h1 plus c1 square by 2 plus gz1 plus q will be equal to h2 plus c2 square by 2 plus gz2 plus work done control volume. Okay, so this equation is called steady flow energy equation. Okay, or this is also called equation of first law of thermodynamics for an open system. When under steady state. Under steady state condition. Okay, since we have already discussed steady flow energy equation, now we will discuss now we will apply this steady flow energy equation for different devices. Okay, so there are various engineering devices which we use in thermodynamics and heat transfer, and moreover in power plant. So we will see them one by one. So let's first device be nozzle and diffuser. Nozzle. Let's consider nozzle first, or we can consider them together. So in case of nozzle and diffuser, the few things have to be mentioned. Assumptions. There is few assumptions, that is the flow is steady state. Okay, and net change in potential energy is equal to 0. That is it is horizontally leveled. Okay, the third point is in nozzle and diffuser there is no work output. Okay, and fourth thing is nozzle is adiabatic. These assumptions, that adiabatic means q is equal to 0. So these assumptions are made before deriving this, the further equation. So if we apply this condition in diffuser here, we can say that our okay, let me write it here again, copy it again, copy, then we will paste it here. Okay, now we will see what these conditions applied here have been satisfied or not. Okay, so first we said that there is no potential energy change, so this should be 0. Okay, there is no heat supplied, that is adiabatic nozzle. There is no work supply. Okay, so we can get the equation is H1 plus C1 square by 2 is equal to H2 plus C2 square by 2. Now if we consider nozzle, let's consider nozzle first. So in case of nozzle, we can see that what happens, let's say this is nozzle. Yes, fluid is entering from this location, exiting from this location, location 1 and location 2. In case of nozzle, what is the purpose of nozzle? Purpose of nozzle is to convert the potential energy of the water in terms of kinetic energy. Okay, it means that C1 is the speed of entry and speed of exit C2. So C1 is very less than C2. Okay, so in generally in case of nozzles, our equation is reduced to C2 square by 2 plus H2 is equal to H1, and from here we can calculate C2 is equal to root 2 times of H1 minus H2. Okay, and one more thing to mention here, generally the unit you should remember, you should keep in mind the unit. So in generally the enthalpy values are given in kilojoule per kg Kelvin, and you require C2 in terms of meter per second. Okay, so what happens that if you directly put in it in kilojoule per kg, so and when you took root, there will be difference of like 1000 multiple of root 1000. Okay, so what we should, like, we can directly write it, the equation is root of 2000 into H1 minus H2. Now you can directly put the values in kilojoule here, and you will get the value C2 in meter per second. Okay, similarly if we talk about diffuser, in case of diffuser it is directly opposite to nozzle, that is it is used to convert the kinetic energy present into potential energy. This is 1, this is 2. So in case of diffuser we consider C2 to be very less than C1. Okay, so we can write it here as C1 is equal to root of 2 times of H2 minus H1. Okay, now moving ahead, we can consider the next device. First we have already discussed nozzle and diffuser. Second device we can discuss turbine and compressor. And so again there are some assumptions here, that is steady state. Okay, second assumption is potential energy change is equal to 0 and kinetic energy change is negligible or 0. Third is adiabatic. Turbine or compressor is also considered adiabatic. If it is mentioned it is not adiabatic, then you can directly use steady flow energy equation and calculate the corresponding values from equation directly. Okay, now this is our steady flow energy equation. So if we look into it, so we can say that this term will be 0, this term will be 0, here this term will be 0. Okay, now we are left with the change kinetic energy also 0, so this will be 0. Okay, so we can directly get equation H1 minus H2 is equal to work CV, work done. Okay, so this equation is applicable in case of turbine. If it is in case of compressor, if we are talking in case of compressor, then what will happen, this will be 0 0 0. Okay, this term is also 0 0, but this work done will be negative here, because compressor is a work consuming device. Okay, so we will get work done CV is equal to H2 minus H1, and this, my friend, is for compressor. Next we will look into third device. Third device is throttling devices. What is the purpose of throttling device? Throttling device purpose is to drop the pressure, or pressure drop in a flow, is used for pressure drop in a flow. Okay. Now there are various types of throttling devices. First one is capillary tube. Capillary tube. So capillary tube is very thin tube which from which fluid is passed. Okay, when passing through the fluid, since the diameter is very small, so the head loss or friction loss is very high, and the pressure of the fluid will be reduced. Next is partially open valve. Partially open valve. Okay. There is one more type, porous plug. In porous plug, a foam is used to reduce the pressure drop of the flow. Okay, and there is one more type, that is orifice flow through is small flow through small constriction or orifice. Okay, so there are few assumptions in case of throttling also, that is closed steady state. Second is change in potential energy and change in kinetic energy is equal to 0 or negligible. Okay, the third is work done. There is no work done in case of throttling. There is no heat transfer in case of throttling. So if we apply the equation, this is the equation, we can get like potential, all the things are 0 0 0 0 0 0. Okay, so what we will get? We will get h1 is equal to h2. So in case of throttling, h1 is equal to h2, so hence it is also called isenthalpic process. Throttling is represented by isenthalpic process on the PV diagram or TS chart. Next, for ideal gas, if we consider this for ideal gas, so we can get T1 is equal to T2. So this will represent that if the throttling fluid is ideal gas, so the temperature initial and temperature final will be same. Okay. Now this there are some properties of this throttling process. So the properties of throttling Okay, so the first property which we can mention is isenthalpic. I have mentioned before. The second is irreversible. Isenthalpic is the process, or throttling is irreversible. It cannot be reversed. Next is, and why cannot it be reversed? As I mentioned in lecture 3, I think, that what is a speciality? I mean, what are the reason behind irreversibility? So I mentioned two reasons. What was the first reason? First reason is availability of friction. Okay, and here exactly that thing is happening. The friction is available in the flow. Okay, like see this capillary tube. So due to the friction here, the availability of friction will be causing the pressure drop. So it cannot be reversed. Process will be reversible. Third is adiabatic process. It is very fast process. So there is no time for heat transfer. Okay, so process is adiabatic. Fourth is there is no work done. Work done during the process is 0. Okay. So up to this point we have completed the analysis, control volume analysis for steady state. Okay. Next we will be moving to unsteady state flow. Okay. So let's start with unsteady state. unsteady state. Okay, so let's again consider system. Okay, so let's say there is a inlet and this is the outlet. Okay, so this is I, this is E, inlet exit. Okay, so let's say that this is system. Let's outline our system. Let's say this is our area of interest, and also we can be said to be control volume. This is control volume. Okay, and there is a certain amount of heat transfer. There is certain heat transfer rate Q dot, and certain work output rate, that is W dot. Okay, let's say Mi mass flow rate entry is at the rate Mi dot, and enthalpy at entry is Hi. Ci is the speed at which the fluid is entering, and Zi is height at which it is entering. Okay, similarly at exit we can define He, Ce, and Ze, and in similar way we can say that the mass flow rate exiting at the rate of m dot t. Okay, so let's say we are considering system for particular time period of t. Before time at time 0, for particular time period t. Now there are some substitute which I will use. I should mention here first. So I will I for inlet, E for exit, 1 for initial condition, and 2 for final condition. Okay, so if we are considering this for time t, so we will start at 0 second, and from 0 second we will observe it up to t second. Okay, so at time t is equal to 0 the condition is 1, at time t is equal to t the condition is 2. Okay, so we will be seeing all the variations that are happening in the system. So let's start with the first variation. First thing we will do is conservation of mass for the system. Okay, so let's start with conservation of mass. Of conservation of mass. Okay, so we can say that the mass dm in Cv can be written as entry rate into dt minus exit rate into dt. So this is a what does dm Cv, so there should be dm dot Cv. So what does that dm, no, it should be dm Cv. So what does dm Cv indicate? Dm Cv indicate that mass accumulated inside the control volume, and how much mass will be accumulated over time dt, that is the dt times of entry mass rate, and dt times of minus dt times of exit mass rate. Okay, so the difference will be the accumulated mass in the control volume over time period dt over a small time period. Okay, now if we calculate rate of change, like rate at which the mass is accumulated, dm by dt for control volume, that will become out to be mi minus me dot. Okay, So this is the equation number 1, which is important. You should remember this. The next equation is like we can solve this. Okay, we can directly integrate this equation. Okay, on integrating from position 1 to position 2. Okay, what we will get, like integrating dm from 1 to 2 is equal to mi minus me dt from 1 to 2. Okay, so dm, if we integrate dm, we will get m2 minus m1, m2 minus m1, and if we integrate this term, then we will get from equation 1 to 2, we will get mi into t, mi dot into t minus me dot into t. Now if we consider this, so we can conclude that m2 minus m1 over a period of total period of t time is equal to mi minus me. Total mass accumulated can be written as this equation. Okay, so you should also remember this equation. This can be directly used in numericals. Okay, now the second thing which we have to consider is conservation of energy. Okay, so let me move it. Okay, so then second point we will be discussing is conservation of energy. Okay, so we will calculate the amount of accumulation energy accumulated inside the CV in time dt. So let's say dE is the amount of energy accumulated inside the control volume. So how will we will like describe the amount of energy stored? We will describe it by, so the energy accumulated in CV, we can write it as is equal to energy entry minus energy exit. Okay, so DECV we can write it as in terms of m dot I into H1 plus C1 HI plus CI square by 2 plus GZI, okay, into dt plus Q dot into dt. Okay, let's change the format of this. We can write it at W network. Okay, minus we can do m dot E HE plus CE square by 2 plus GZE dt plus W dot into dt. Okay, so this is our conservation of, and this will be, let's consider like this. Okay, in EI minus EE. Okay, so on if we consider like potential energy and kinetic energy changes to be 0, so we can directly obliterate these terms. Okay, so we will get from here, we will get dE by dt for CV, rate of accumulation, energy accumulation in CV will be equal to du by dt for the CV, and that will be come out to be m dot I HI plus Q dot minus m dot E HE plus W dot. Okay, so this is our equation for energy conservation. Okay, now we can directly integrate this equation and further derive it. So if we integrate this equation, we can get integration of du from 1 to 2 is equal to integration of m dot I hi dt 1 to 2 plus integration of q dot dt minus integration of m dot e he dt minus integration of w dot dt. Okay, so if we consider hi and he as constant, so if we consider hi and he to be constant, that is irrespective of constant with time. Okay, that is irrespective of time. With time hi and he value does not change. So what we can do, we can directly take it out of the brackets and we can write it as u2 minus u1 is equal to hi into mi. So we will left with the with integration m dot I dt. So m dot I dt integration can be written as mi. Okay, plus again the total heat supplied minus here it will be he me minus total works done. Or we can this equation can be directly used in the subsequent questions which we will be doing. Okay, now these two equations, you can say either equation this or this, or this or this. So these two equations, let me mention these two equations. These are the main equations. You can always derive the next equations by yourself. Okay, a and b are the main crux of study of unsteady state flow process. Okay, now we will in next session we will be doing some questions on this unsteady state, and we will be using these equations to solve our question. Okay, there is few more things. Let me tell you a few more things. Okay, so one the most important thing now is next topic, that is mixing, adiabatic mixing. Mixing of fluids. Okay, adiabatic mixing of fluids. So in adiabatic mixing, during any mixing problem which is given, that is mixing of gases problem, gases or fluids, whatever. If it is for fluids, you have to consider few points. Let me remind it. So whenever there is mixing of fluid, you can directly equate the energy. Okay, so energy initial equal to energy final. Okay, you can say that energy at state 1, like energy initial, is equal to, if there is a mixing of the fluid, let's say, so you can say that, let's say two fluids mix, E1 plus E2 you can do is equal to E3. Both after the both mixes they supply energy E3. You can do it like this for fluids, if the fluid is liquid. Okay, now if this fluid is gas, so if it is given that adiabatic mixing of gas, okay, or gases, of course there will be multiple gases for mixing. So there are 3 points which you should remember. This is the important point. The first point is you should use state equations. Okay, so that is you have to link all the properties given. Okay, second, you should apply conservation of energy. Of energy That is also our first law of thermodynamics. First law of thermodynamics. Okay, and the third most important point is you have to apply conservation of mass. So by using all these three conditions, you can solve all the mixing problems. Okay, so I think that will be it for the today's lecture. We will in next lecture we will solve some questions, and we will also see how these three conditions are used in question. Okay, now thank you for today.